Testing the mic system first. Make sure I'm on. Testing the mic system first. Make sure I'm on. Testing the mic system first. Make sure I'm on. All right, we started the other day, so before we go on, let me make sure my pins can be rotated through. Yes. Looks like they can. So let me do a quick semi-important review and tell you that I may be going to material that is a little ahead, but also I will be going back to some of the other material. So don't get discouraged if you feel as though I've gone past where you are, because I will be going back. Here's what I mean. Hang on. When it comes to beams, I need to make sure, we understand how to get internal forces. So I'll be going back there. I'll be going back a little bit to trusses. But for the moment, I'm going to go forward a little bit. And if you remember, or if you watched the previous lecture, we started finding centroids, X bars and Y bars. Now, there's two ways to think about this, and that is, hang on, let me get this out of here. One way is to think of it as a composite. And the other is if, in fact, you had, you had a function. So this is if you have individual blocks, or say building blocks, or where you can make a composite. This one is if you had functions. This is a basic thing, always works. Over here in composites, only works if you have the information from each of the composites. For example, if you had two blocks that were nailed together here, and what you wanted to do was you wanted to find the centroid of this, you have the choice of having these two blocks, or these two blocks, or you could be so silly as to do those three blocks. So if you do those, you'd find the centroid here and here. And then you would go through this formula. And by the way, if you want to find the Y bar, it looks like this. Not too surprisingly. If you want to find the Y, you do like that. We did a bunch of those on, I believe it was Monday. We sort of poked around. What we're going to do here is a few of these, and then we're going to go on to something extra here. Let's find, okay, so here in fact is the book. Now, in this section, okay, here, somehow it jumped forward. So this is chapter 9, And in this, he has several things. He wants to find the center of gravity, center of mass, and the centroid of a body. So he's doing everything. So it's essentially the kitchen sink. But in essence, this is very true, very possible. I mean, you really do need this. You need to find the center of mass, and some extra information for dynamics. You have another reason for finding the centroid, or the center of mass, or centroid of a body for mechanics of materials. So there's reasons for finding all of these. It leads you through a wide variety of things, but you'll see a similar component here in everything, barring this, which might change from concept to concept. Here you're looking at the weight, where that's the W. Center of mass. Now, if it's homogeneous, you might find that these things are the same. So what you'll notice is this. These are different. Centroid of a volume. Guess what? This is different. But you'll notice this, the basic structure is the same no matter what. In actuality, sorry for the delay, this is the fancier computer, and I did not switch it out, which I will try to do that before next time. The interesting thing is, in order to integrate over a mass, usually it's broke down to a volume. Usually to find a weight, it's broke down to a volume or an area. And I can't go any further back because there is no further back to go. So we moved on in the lecture we had to finding the centroid of an area. And if you look at it here, here he just tells you, here's some sort of function. We want to find the centroid. It's going to be called X bar and Y bar, always is. So you can do this in two ways. You can set a vertical bar or you can set a horizontal bar. The vertical bar, the area would be this times that. Over here is going to be this times that. X dy. Now, what's interesting is you're looking at this and you're like, hey, wait a minute. This is not the same. But here you would put in this, and over here you would put in y as a function of x over here. Therefore, you could carry out the integral that's sat here or here. Now, you have to be very careful here too, because the way he's constructing these, there is well, we won't talk about that one till we get to the volumes, but there is if you're looking at an area, usually you can write it this way. And something, for example, if you came back here and you took yourself a little block and you said dx dy, and you move this block all around. So as you move it all around, of course it can't go lower than here, and it can't go above this, and it can't go anything to the left of here. So you have to respect your boundaries, and that's where this thing can become complex, or sometimes not so complex. Depends on the problem itself. This one, your limits of your integration, if you're looking at the dy, for example, it's going to go from the bottom here to this function. If you're looking at dx, you're going to go from here over to here. So you have limiting factors on both those. Depends on how the person in calculus did this for you, but this is a easier standard here. But either way you do it is fine. Then he says centroid of a line, or, that would be like a clothes hanger or something bent around. And then he goes through some procedures, and he does a few like this. Those are okay. Those are not exciting. Those basically rarely come up in the real world. Here he's got another one. So this is a standard one here, determining the centroid of a triangle. He did it generically. The other day, I did it specifically. I think I did, something like 2x, y is equal to 2x. So I had a triangle set right there. What you find out, and this is always the case, it's a third from the heavy end on both sides. So here's the heavy end on both sides. Here's the triangle area. That's easy enough. If you take an integral across here, take half of that. This is the triangle area, the blue. Nothing fancy, nothing new. Here you have a case in point in which you're integrating, and this time he decides to use a d theta. So in essence, what he's doing, he shows it on the diagram correctly. He's basically taking this little center gray section here, and he's integrating it from one angle all the way to 90. Or pi over 2. I should have said pi over 2. Here, I think we actually did this one in the class, I may have put a constant in front of there. I don't know. You integrate it around, you get the x bar and the y bar. Nothing really fancy there. So this is just a bunch of set of integrations. Now, you'll see a lot of these problems will require you to integrate, as you can see. Some of them are harder than others. Now we're into this concept of composites. Now, again, composites of what? The weight or the mass? Oh, he doesn't describe anything but the weight, but he should say the mass, the area, the volume. So in other words, okay, let me go back to this. He actually should complete this out. This could be the weight, could be the mass, could be the volume, could be the area. We're going to basically work inside the concept of area because it's 2D. The volume, the mass, and the weight exists mostly in 3D. So, and it's, okay, so he says that, but he goes and does this problem. So here's a typical problem. And what you'll see is it's just like a Excel spreadsheet. Here's what I mean. If you're looking for x bar, it's equal to the sum of the x bars inside of each of the composites times the sum of the composites. So what does he do? He sets up a table to handle that. Then he sets up a table and he says, hey, I got 3 segments. I've got a triangle here. I got what appears to be a square, but yeah, it is a square. It's directly a square. What he's done is he's extended that, and he's considered this one as item 2. Then what does he do? Well, he says, I'm going to subtract off this part, which is number 3. The 3 will be this part right here that I'm going to extract out of here. So, amazingly, it works fine. Okay, so here we go. He listed his X bars, so he found each one of them, and his Y bars. Now you have to make sure you put this exactly where it needs to be, meaning it has to sit exactly in this spot to subtract that whole out. So it's 2.5 over to the left and 2 up to the centroid of that. And so And the other thing you have to do is you have to respect and use the coordinate systems. So this is why there is a minus here, and a minus here, and there's not a minus in the y, because the whole thing is above the y plane, or the y is equal to 0 line there. So you have to respect the coordinate system. But notice what happens here. In segment 3, he delineates this as being a minus area, meaning you're sucking it out of there. You're subtracting it out. And what does he do? In his Excel spreadsheet kind of thing, he goes over and he multiplies this column to that and puts it right here. So he says this times that goes right here. Then he says this times that goes right here. Then he says this times that goes right there. And likewise on all the rest. In other words, the y column, this times that goes right there. This times that goes right there. And these last two. This time it is a minus here. So you have a minus term here and a minus term here. So you just add them up as they sit. So you sum this column down. Here you get 14, there you get minus 4. You sum this column down, and then guess what you do? You just divide them. So what does he do? He divides this by this 11.5. And then, he divides this by the 11.5 again. He gets the actual centroidal location of this weird little block here. And it's just simply an Excel spreadsheet. If you could just do that in your mind, you'll find it works out very nicely. So even with this one, which this is a mass version here. And again, he does the same thing. He breaks it into 4 segments. He starts with this pointy cone. Okay, you have to look at the solid again. He actually locates the center of mass of the assembly. There's a density, and a hemisphere has a density. Oh, there is a 22 cylindrical hole in the center. So this is a drilled out hole. I was about to say, why does he have the 4th one? This is your hole. This is something you're clipping off the top. This is the 2 things. So imagine, if you will, you're creating a CAD drawing. And what you do is you subtract, you make the cone, and you make the half sphere. You put them together. Then you cut the cone off. And then you cut the hole out. So what you're going to have, believe it or not, is a minus mass for number 3, because it's a cutout, and number 4. And then you found your centroid, or your Z, which he's only interested in the Z, this component. And so you just do your Excel spreadsheet. This times that goes here. This times that goes here. This times that one goes here. And this one times that one goes there. Sum them up. Sum this up. Divide them. And you've got your location. So composites are just basically Excel spreadsheets. You can look right here and see, well, locate the center of mass of, like, say, this one. Well, my center of mass of this big block is going to be, let's see, 5, 6, 7. So it's going to be 3.5, but it's also going to be buried 1 into this block. And then this one, the centroid, is on this face, but it's going to be pushed back into the block 2 feet. So it's going to be 1 foot over, 1.5 foot up. Now, what you have to do is you have to respect the coordinates, and you can place all that together. In fact, what time is it? Maybe I've got enough time to do just that one. Let's do that one. Okay, hang on. Okay. I really don't need the text around it because all I know is I'm finding the center of mass. So Control S. Okay. Hopefully we got it. Okay, and what I'm going to do is just drop it, say right there. Oh, it's a lot larger than, but I can squeeze it down. Okay, so I've got, in this particular case, I've got an X bar, I've got a Y bar, and a Z bar. Okay, so I'm just going to write them out. But they're not areas now. They're volumes. And likewise for Z and Y. So here's what I'm going to do. I'm going to identify two sections, this one and this one. So my Excel spreadsheet will be like this. And I'm going to do my volumes. So for the volume of 1, I got 2 by 6 by 7. 2 by 6 by 7. And you know what? I'm going to move this down so I can have room to write the information. I can write the equations above. And okay. And that's supposed to be a V. A V's. Okay, leave plenty of room. I am going to look for a sum here, 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 which I didn't give myself much room for the Y for some reason, but I can make it happen. Let's look at the volume of this section 2. This is 2 by 3 by 4. 2 by 3 by 4. Double check myself on the first one, then I'll double check myself on the second one. Second one, 2, 3, and 4. 2, 3, and 4. First one, 2 wide, 2 this way, 6 this way. What's the dimension that? 7. Okay. I know I've got a fancy calculator on the computer, and it's actually, no, it's not up. But 2 times 6 times 7 can be done here. So I get 84. 2 by 3 by 4, 24. Now comes the part where I have to really kind of look at this. If I look at, and I can do them one coordinate at a time. So I'm looking out the X direction, and I'm finding the centroid of each block. Well, the first block, I have to remember this was my first one. This is my second one. My first block is just 1. The second block is 2 and then half of 4. So that'd be 4. Now, I'm looking for the centroids out in that direction. Okay, I'm going to do this. Well, I'll do the first block first. It's 7 all the way out, so it's 3.5 to the centroid in there. And then looking at the second block, that's the easiest. Remember, we're still looking at the Y bar. I go halfway the distance, and so that'd be just 1. Now, Z block, that's going up. Z of block 1's half of that, or 3. And then half of that one, or 1.5. Now, I can populate this. I don't need to look at the geometry anymore. 1 times 84 goes here. That's 84. 3.5 times 84 goes there. Okay, so give me a second. I have to bring my calculator up again. What would I say? 3.5 times 84, 294. And then 3 times 84 go into here. 252. That was supposed to be a 4. Okay, now 4 times 24 goes here. I should know that, but I just want to make sure. What? See if I can get that out of there. Okay, 1 times 24, that's easy. 1.5 times 24, that should be 36. Now I just sum 84 and 24. Uh-oh, did I mistype that? Okay, 84. No, I didn't. Okay. So the total volume of this whole blue block is 108. Now, 84 plus 96, 180. And then these two, 294 plus 24, 318. So I guess I really didn't need the wide column. 252 plus 31, 283. Now, all I need to do is X bar is equal to this one over the total volume. Y bar is equal to this one over the total volume. Total volume being this one. And then Z bar is 282, 283, 108. Long equal sign. And my phone went off again. All right. 180. 180 divided by 108. 1 2/3. 2.94 repeats. And 283 divided by 108. 262. And then some repeating digits after that. So that's it. There's nothing more to these. They're just composites. That's all they do. You can get to the point you can solve one. You can create a spreadsheet and solve as many as you want. This composite mentality will become handy in the next chapter, which actually is as, if not more so important than this one. And in my mind, they should have been combined, but it would have been hard to do that. So here's a beam's cross-section area. So let's look at this. Now this, how much time do I have? I got enough time to do this. This one is interesting because it's a 3D object, but you're doing a 2D cross-section. Okay, and the reason I'm picking this one is because when you get to the second moment of the areas, that's kind of what you're doing too. You're taking a cross-section of a three-dimensional object. Essentially, you're slicing it. Now, there's another time you sliced it, and that was back when you were doing internal forces. And these two things go together, especially Chapter 10 and that slicing of the internal. And I'm going to try to cover that next Friday. During the week, I'm not going to talk about that. I'm going to try to make common sense of that. So I am waiting for it. Not a fast machine, yet it's faster than the other one, supposedly. Okay, there we are. So this time, what are we doing? He wanted to find, well, first let's go back and make sure we know exactly. Find the location of the centroid Y. So that's basically here. So we're going to basically measure from here. This will be our Y coordinate. He wants to know the centroid. There'll be a reason you need to know that, and it'll become clearer a little bit later. Okay, hang on. All right, let's go back to... So, same exact concept, except you're only interested in y. And we're going to measure y from here. Sum y bar of each section. And so I'm going to label this as section 1, section 2. Oh, and section 3 is the same. So, here we go. Let's take this thing and start our Excel table. Here's our 1, here's our 2, here's our 3. And we really don't need this. Maybe I better move these over. Okay, here we go. Area. You know what? I guess I'll carry them as the hundreds. Okay, number 1. Number 1's area is 50 times 400. So there's 3 zeros, and 5 times 4 gives you 20. So I hate that there's so many zeros here. What's the y bar to there? Well, you go up 200, and then you go up to 25. 225. Because you're halfway, your centroid of this spot, of this number 1, is about right here. That's pretty big. We're assuming each of these pieces of wood are homogeneous. So, there you go. So there's no big holes in them. So this is right in the center. Oh, that's weird. Okay. So it's 25 up, or half of the 50. I'm not even going to do this yet. So let's hit section 2. It is 50 wide by 200 tall. 50 wide by 200 tall. 1, 2, 3 zeros, and then a 10. So it's a lot of millimeters squared. Where is y bar to that? Well, y bar is halfway up, or 100. And guess what? This is exactly the same, because it's, the same distance this way. So now, let me just break out my calculator, I guess. I'm not going to attempt to. Okay, let's see. 20,000 times 225. Oh my gosh. Okay. Okay, got a million here. I better keep track of my zeros, or else I'm gonna mess up. Okay, so let's sum this box. 20,000. And there's 2 10,000s. So just give me 40,000. And over here, I get 2 million, or 6.5 million. All right, so my y bar is equal to, again, sum of the y bars for each individual. I equal 1 to, in this case, 3. So this should be, if you want to be very mathematically rigorous, that's what this thing should actually say. And this should say I equal 1 to 3 of all the areas, but it's equal to 6.5 million. Well, okay. Divided by. Okay, calculator went back off. Make sure, luckily my calculator puts the commas in there to help me find out where I'm at. It says y bar is equal to 162.5. Does that make sense? And this is something you should think about. Okay, so it's at least 100 to the, it's 100 to the center here. Since this is fairly significant, 400 versus 200, it'll draw that centroid up towards it. So it is greater than 100. It's not greater than 200. If I got a number here that was greater than 200, I would be a little bit suspicious, although it could be, but especially, I'll tell you how it could be, is if you had two slivers stacked, ooh, this is bad looking, on something very tall, it could draw the centroid up onto the body here. But for the case in point here, I'm satisfied that we're reasonably close. So in essence, what you got is, again, just the mentality of making a kind of a table, Excel spreadsheet kind of thing in your own mind, and just calculate it, sum it, divide it. And that's pretty much it. That went faster than I thought. Okay. So let's keep going. The rest of these are just the same thing over and over. You could look at composites of all sorts of materials. You could break, if you're breaking these down, you could figure out how you're going to break it. I could break it as a big block, like so, and subtract off the triangle. You could do that as well. You could take a big square here, subtract this one off, subtract this one off. Oh, this is a tricky one. Well, he says neglect the size of the corner of the welds at A and B. So from that, to me, he's assuming that he takes this object, sticks it right on the top of this object, and then some guy or girl comes and welds a big weld out here. And so, to me, he's saying that your object is this with a circle touching it. Kind of cheating, but it's a good approximation. You might find these little areas here to be insignificant anyway. So this little part here might be insignificant if you really calculated it. Here's your just simple I-beam. You want to find the centroid of this I-beam. So this is what I'm talking about. When you're finding the internal loads a few chapters back, and you were saying, okay, I got a beam that's loaded this way, supported here. What's the internal load at section C? Well, yeah, you take section C here and you find it. Once you find the internal load, meaning the moment and the shear, then you need to find out how these are related to the stresses internally to the beam. Centroid, finding the centroid of that section, in other words, a beam that looks like this in its section will behave significantly different than a beam that looks like that in its cross section. So it's important to actually know what these sections are like. Once you slice it, what is the shape you're slicing? I'll talk a little bit about that next Friday as to how this kind of goes together with mechanics and material to give you an idea. And you just go on through this. Oh, here's something interesting. So here he's got something like this. Hang on. But he's telling you, here's an object. You're not integrating it, but you're taking a composite of it. But what does he do? He tells you the centroid locations of certain places on it. And you notice the frame itself is number 3. It weighs a lot. The mechanical components, or the motors, are number 2, and they weigh a decent amount. The front and the back tires have a weight. And from all that, you should be able to find where in this whole thing the centroid would be, or the center of weight. It would definitely not be here, and it definitely not be here. It would be drawn, these 2 points being heaviest would draw them towards them. The frame itself is going to draw the most, so it's going to be closer, or pretty close to this, because it's fairly heavy there. And he gives you the X and Y locations of every single point there. Okay, so, okay, we're not going to deal with that. And we go on to the, what was that? Oh. Okay. Okay, now we're looking at moments of inertia. And that, what am I? I'm looking at 5 minutes left. But let's just look at the basic function here. If you looked at it in a functional standpoint, you would notice in the previous section up here, or maybe, okay, so in the previous functions, you found that you were having to integrate. Let's look back where I wrote initially. You found you were having to integrate, and you can look at this last Monday's lecture, in which you say had a function that looked like that, and you're just integrating it. So you're integrating y, and you're looking at this, say your sliver goes out here, it's dx, and then you go up to this top spot. So you just have an integral that looks like that. So in your second moment, guess what he has? And, oops, it's supposed to be an I. And actually, the technical representation is supposed to have 2 x's, but in the early phases of this, you're learning the material, he puts it XX. Now, if you look at, he just puts an X. Now, notice something interesting later. Okay, after the parallel axis theorem, we move up to, and possibly, maybe it's in the next section. Okay, let's move on. Okay. Oh, he goes straight into composites. Okay. Huh. Usually they add a section here, and maybe I just missed it. Let me go slower. Did I miss it? I may not have missed it. Well, the reason I like to carry both terms is there's the possibility, although not presented here, of this, where you have an X and a Y. And so apparently what he's presenting is these terms. And so what we'll do on, was it Monday? Yeah, on Monday, we'll start taking some common terms and we'll start integrating those. And we'll start seeing some behaviors. One of the most common that you'll know by heart will be a rectangular section. Mostly because you can stack rectangles to make I-beams, C-channels. If you get into the shop and you have a big flat piece of metal that you've ordered, you can do a lot of things to make a beam out of that. You can make a C-channel. You can have different variants of that C-channel. You can do all sorts of things like that. So with that, these are common shapes, and so we'll do a square, or I guess actually a rectangle, and we'll do a triangle on Monday and show you how those develop out. But we'll also look at doing some weird functions, and they're not that hard. The material and the way he presents it here is a little bit different than the way it was presented in Cal 2. Or maybe that was Cal 3. Anyway, one of the calculuses. So I like to use the mathematical representation a little bit more. And I'll try to show you, it may take 2 class periods, to show you that actually you get the same answer. It really doesn't matter. So I'm going to say we're done. And we'll just say we're done.